A single geometric object existing in 196,883 dimensions possesses more distinct symmetries than there are subatomic particles contained within the entire planet Jupiter. This is the monster group, the absolute largest sporadic finite simple group known to mathematical science. In the realm of abstract algebra, finite simple groups function as the primary atomic building blocks for all finite groups. They contain zero non-trivial normal subgroups, meaning they cannot be decomposed or factored down any further, acting similarly to prime numbers in standard arithmetic systems. The definitive classification theorem of finite simple groups proves that every single finite simple group belongs to one of four primary categories. Three of these categories represent infinite families of mathematical structures, while the final category contains isolated, highly unique exceptions that do not fit standard rules.
These three infinite families comprise the cyclic groups of prime order, the alternating groups of degree 5 or greater, and the complex groups of Lie type. The exceptional outliers are exactly 26 isolated structures collectively designated by mathematicians as the sporadic groups. 20 of these sporadic groups reside within a closely knit hierarchical network termed the happy family, which structurally peaks directly at the monster group. The remaining 6 isolated sporadic groups lack any structural connection to this hierarchy and are consequently called pariah groups. Mathematicians Bernd Fischer and Robert Griess independently predicted the existence of the monster group in 1973. Because the structure was far too vast to simulate on contemporary computer systems, proving its actual existence demanded a direct, manual algebraic construction from scratch.
In 1980, Robert Griess successfully constructed the monster group entirely by hand, completely avoiding any computer assistance. He achieved this monumental feat by defining it explicitly as the automorphism group of a highly specialized, complex mathematical structure now known as the Griess algebra. The Griess algebra is a non-associative, commutative algebra that operates across a real vector space of exactly 196,884 dimensions. The monster group operates by perfectly preserving the unique multiplication rules established within this massive multidimensional space. The total number of elements, or the order of the monster group, is roughly 8 times 10 to the power of 53. Written out fully, it forms a 54-digit integer starting with 808 septillion and ending in thousands.
The exact prime factorization of this immense order reveals its deep structural blueprint. It is composed of 2 to the power of 46 multiplied by 3 to the power of 20 multiplied by 5 to the power of 9 and 7 to the power of 6. The remaining prime factors include 11 squared, 13 cubed, alongside single instances of 17, 19, 23, 29, 31, 41, 47, 59, and 71. These 15 unique prime numbers represent the foundational components dictating the internal arithmetic of the group. The 15 specific prime numbers that divide the monster group order are precisely classified as supersingular primes. This precise mathematical property connects the monster group directly to modular curves and the complex arithmetic governing elliptic curves within advanced algebraic number theory.
The monster group cannot be faithfully represented by matrices in any complex linear dimension lower than 196,883. This absolute minimal representation establishes the lower boundary for visualizing its geometric footprint within linear systems. Linear representation theory maps abstract group elements directly to invertible matrices, effectively translating complex symmetry operations into standard linear algebra. For the monster group, computing these irreducible representations required calculating an exceptionally vast and mathematically dense character table. The resulting character table of the monster group forms a massive square matrix measuring exactly 194 rows by 194 columns. It systematically catalogs the precise mathematical traces of the irreducible representations across all distinct conjugacy classes.
In 1978, mathematician John McKay observed an entirely unexpected numerical coincidence. The dimension of the smallest non-trivial matrix representation, 196,883, appeared embedded within the core coefficients of a completely unrelated modular function. This specific coefficient belongs to the classical Fourier expansion of the Klein J function, a highly symmetric modular function utilized heavily in advanced number theory. The first non-trivial coefficient of this J function is precisely 196,884. McKay noticed that this modular coefficient precisely equals the monster group's minimal representation dimension plus 1. This seemingly accidental matching strongly hinted at a hidden, deeply profound connection linking the separate realms of finite group theory and complex analysis.
Mathematicians John Conway and Simon Norton thoroughly expanded this singular observation in 1979. They discovered that subsequent coefficients of the Klein J function were exact linear combinations of the monster's representation dimensions, officially naming this mysterious mathematical phenomenon Monstrous Moonshine. The whimsical term moonshine directly reflected the widespread skepticism among contemporary mathematicians. The implied relationship between the largest sporadic simple group and complex modular functions seemed completely wild and highly improbable, as no unified mathematical theory existed to bridge them. The necessary explanatory bridge was eventually discovered within theoretical physics. Mathematicians Igor Frankl, James Lapowski, and Arnie Morman constructed an infinite-dimensional graded vector space utilizing vertex operator algebras, structures that naturally and inherently possess the complete symmetry of the monster group.
Vertex operator algebras mathematically formalize the complex algebraic structures found within two-dimensional conformal field theories. In quantum physics, these conformal field theories are utilized to model and describe the intricate worldsheet dynamics of strings propagating through space-time dimensions. In 1992, Richard Borcherds deployed this advanced vertex operator algebra framework to definitively prove the long-standing Monstrous Moonshine conjecture. His revolutionary proof utilized generalized Kac-Moody algebras, earning him the prestigious Fields Medal in 1998 for his achievement. Borcherds demonstrated that the monster group effectively serves as the primary symmetry group for a specific physical string theory model. It explicitly stabilizes a quantum bosonic string moving through a 24-dimensional space that has been mathematically orbifolded by the Leech lattice.
The Leech lattice represents an extraordinarily dense and optimal packing of spheres within 24 dimensions. This specific geometric configuration is essential for optimizing error-correcting codes in telecommunications data, and its internal symmetry group directly connects to the monster group structure. This specialized physical model is formally classified as the monster conformal field theory. Within this quantum framework, the complete partition function of the physical theory matches the Klein J function exactly, explaining why its coefficients systematically encode the structural dimensions of the group. Modern quantum gravity research actively applies the monster group to investigate the properties of three-dimensional quantum black holes. Renowned physicist Edward Witten suggested that pure quantum gravity operating within a three-dimensional spacetime is holographically dual to this exact monster conformal field theory.
Under this physical hypothesis, the individual quantum states of the monster conformal field theory correspond directly to microscopic black hole states. The immense size of the monster group directly dictates the thermal entropy calculation for these highly theoretical black hole models. The internal architecture of the monster group contains an extraordinarily vast variety of subsymmetries. Investigating these complex subgroups allows modern algebraists to accurately map out the mathematical geography of the smaller sporadic groups that remain embedded directly within its overarching composition. Identifying and classifying all maximal subgroups of the monster group has stood as a monumental challenge for computational algebra. By isolating these maximal boundaries, mathematicians can completely map out the diverse geometric transformations and actions available to the monster group.
The monster group emerges within modern arithmetic geometry through the application of Belaï's theorem. It can be explicitly realized as a Galois group over the rational numbers for unique geometric coverings known to mathematicians as dessins d'enfants, or children's drawings. The verification of Monstrous Moonshine subsequently inspired the generalized moonshine conjectures. These advanced theories extend the mathematical relationship from the core Klein J function to a wider family of modular functions linked with various specific subgroups of the monster group.
Expanding well beyond the monster, contemporary mathematical research has successfully identified umbral moonshine. This framework connects the remaining sporadic groups to mock modular forms, definitively proving that the monster group was not an isolated anomaly, but part of a unified paradigm.
Despite its truly staggering scale, the entire monster group can be generated using only two of its individual elements. Pinpointing and analyzing these specific pairs of generating matrices remains a highly active area of study within modern computational group theory. Accurately visualizing a geometric structure existing within 196,000 dimensions is physically impossible for the human brain. Mathematicians rely heavily on advanced computer algebra systems and complex projection matrices to slice this multidimensional space into comprehensible three-dimensional representations. The monster group is classified as a Hurwitz group, meaning it can be generated by two elements satisfying highly restrictive algebraic constraints. This unique property links it directly to Riemann surfaces, possessing the maximum possible degree of symmetry relative to their geometric genus.
Theoretical physics models explore whether the monster group restricts the specific gauge symmetries permitted within fully unified field theories. Certain hypotheses propose that the fundamental low-energy physics observed in our universe is deeply constrained by these massive, exceptional mathematical structures. Although currently impractical due to intense computational overhead, the vast non-abelian configuration of the monster group offers innovative theoretical frameworks for constructing advanced cryptographic protocols. These algebraic protocols could potentially provide resistance against quantum computing brute force decryption methods. Processing complex matrix operations inside the monster group requires highly specialized algorithms. Utilizing generalized fast Fourier transforms optimized for finite groups allow researchers to efficiently analyze massive datasets and complex permutations across these expansive, multidimensional mathematical fields.
Projecting the 19,000-dimensional representation space into three-dimensional coordinates reveals highly intricate, fractal-like distributions of its symmetry axes. This stunning geometry illustrates the remarkably organized and rigorous distribution of elements occurring throughout the entire sporadic algebra system. As the definitive crown jewel of the classification of finite simple groups, the monster group stands as one of the most complex entities ever discovered. It continues to successfully unite completely disparate domains of pure mathematics and theoretical quantum mechanics. Ongoing investigations focus on the deep intersections between the monster group and the geometry of generalized Kac-Moody algebras. Understanding these interfaces allows researchers to explore the outermost limits of symmetry, redefining how algebraic structures model physical constants in nature.
Decades after its discovery, the monster group remains an active frontier of discovery. It underscores a profound philosophical reality in modern science. The most complex configurations of abstract symmetry are directly hardwired into the core laws governing quantum spacetime.